How can we capture, reconstruct, and interactively render realistic depictions of real-world places, specifically for indoor scenes with large geometry and reflections? Hello, my name is James Tompkin. I'm an assistant professor at Brown University. Today I have the pleasure of introducing our approach towards solving this problem: scalable neural indoor scene rendering. This is the work of Xuqiao Wu and Jiamen Xu, co-first authors at Zhejiang University, supported by Zihan Zhu and Hujian Bao, and led by Weiwei Xu, with Qijing Huang at UT Austin and myself in support. So, reconstruction and novel view synthesis of the real world has long been a key goal of visual computing, for example, for the creative industries, for games, and for VFX to edit real-world depictions. It is also critical for virtual and augmented reality, and for immersive telecommunications to reduce our travel carbon footprint. A preliminary step is to sample the scene with an RGB camera, and for large scenes this will produce hundreds or low thousands of images. Then we perform photogrammetry via structure from motion and surface reconstruction to create a mesh of the scene. Oftentimes we call this a geometry proxy, especially as its accuracy reduces. To create novel views, we can use image-based rendering to project and blend the input images onto the geometry proxy. Modern approaches use deep features to improve quality, but this can lead to luminance flickering or unstable reflections because the density of input sampling is not sufficient for these interpolation-based approaches. More advanced material and lighting modeling can improve the quality of reconstruction and allow sophisticated effects such as relighting, and this can also be improved through neural reconstructions too. But the appearance of reflections is still tricky from sparse inputs, and complex object geometry can also suffer, such as the table lamp in the background, because the recovered geometry proxy is inaccurate. Our step towards our community's goal produces stable reflections on planar surfaces and more accurate geometry, such as on the far table lamp, overall improving reconstruction and rendering quality. This technique is a scalable neural reconstruction method based around a hybrid neural field for geometry and appearance. While our appearance model doesn't allow relighting, it does improve rendering of the scene as captured. Compare the geometry of the far table lamp and the quality of the floor reflection. To achieve this, we tackled 3 of the current problems with applying neural reconstruction and rendering techniques. Let's take a look. We begin with neural radiance fields, as have taken over the academic world. NeRFs and their many variants are excellent at interpolating view-dependent appearance from input images, such as from unstructured but dense arrays, like in blue here. Problem number 1. Scene detail is limited by the capacity of the MLP. When we cover a large scene with more input images, we often find missing or reduced quality image features, especially around reflections, like the wood floor tiling. If we increase the MLP size, both optimization and rendering take longer. Problem number 2. Reflections are difficult from sparse inputs. In dense forward-facing capture, the same reflection is present in most images, but in sparse room captures, reflections may only appear in a small subset of images. Here's an example. In the artwork, the reflection of the lamp is visible in only 8 of the 27 input images, leading to a missing reflection in the reconstruction. Problem number 3. Rendering is slow. For large scenes, many points along array must be sampled, and speed only decreases if we must increase MLP capacity to cope with large scenes. So in summary, current techniques struggle to scale to large indoor scenes, both to maintain quality at reasonable optimization and rendering times, and to cope with sparser samplings while maintaining reflections. So you might be thinking, well, I know how to scale things. Tiling. Then I can also parallelize easily. And yes, tiling is an effective generic solution to many 2D computer graphics problems, but tiling in 3D spaces with radiance fields is trickier. We could forego the MLPs and optimize a voxel structure that stores view-dependent radiance using something like second-order spherical harmonics. This doesn't require any MLPs, but it does use a lot of memory per voxel, leading to a scale-detail trade-off. For instance, the second step of planoxels requires fine-tuning the entire voxel octtree at once. This requires the whole space to be in memory, and can lead to out-of-memory errors on large scenes. Okay, so what if we kept the compact MLPs but tried to train one MLP per tile? Well, an output pixel depends upon points sampled along a ray that intersects multiple tiles, and the longer the ray, the more points we need to sample. During optimization and inference, we need to access many different MLPs for a single pixel, making scalability and parallelization difficult. One example here is KiloNerf. This uses a whole scene nerf MLP as a teacher to then train many tiny NLPs, where each is responsible only for scene points within it. So while this can accelerate final rendering, as the cost to evaluate the MLP of each sampled point is reduced, we still have an optimization that depends on the whole scene MLP. So what could we do? Well, what if each MLP encoded its own background? That would make each tile MLP independent if we assigned it all of those points along the ray, but that's also not scalable as there are too many points. We don't know where the background is. So what could we do? Well, let's leverage the initial photogrammetry, we call this the global mesh, to conservatively define where the background is, sample an interval around that with a fixed number of points, and then assign these points to each of the tile MLPs. This leads to a scalable and parallel solution without restricting the quality of the optimized geometry to that of the global mesh. Here are some examples of sets of reconstructed tiles. Each tile is trained in parallel and then here rendered together as a group. Background sampling also improves reconstruction accuracy as it allows an individual tile to more easily disambiguate the location of radiance within the volume. Without background sampling, we see blurring from phantom volume density. With it, we see improved reproduction of the window shutters and the coffee table books. And just to show that the global mesh only guides the reconstruction, through depth renderings of the volume, we can see the improvement of the recovered geometry that contributes to our improved rendering quality, such as on the plant, the chair leg, and the far table lamp. On to problem 2, that reflections are difficult to recover from sparse inputs. For this, each tile contains two MLPs, one to encode density and view-independent or diffuse appearance, and one to encode view-dependent appearance like highlights and reflections. For this, each coordinate maps to density and a set of second-order spherical harmonic coefficients. The final pixel color is simply the sum of both integrals after resolving the spherical harmonics. This separation idea has been used numerous times before in image-based rendering to compactly represent reflections. For us, we will see that separating simplifies the function that the reflection MLP has to estimate. But we can also use another trick here to help us. So, storing spherical harmonic coefficients for combined appearance at a surface location can be redundant. Consider a plane, like the wooden flooring, reflecting a ceiling light. The spherical harmonic coefficients at this XYZ location will be different from at this location because the diffuse texture is likely to be different. But the illumination is similar, and it's likely that the highlight reflection will have similar appearance. Separating diffuse allows us to combine two simpler functions instead of one more complicated function. But we also gain access to a second benefit. If we resolve the paths, we see that a virtual reflection underneath the surface could represent this illumination. During optimization, we ask the MLPs to determine where best to place reflected light at these virtual path length locations underneath the global mesh. Here's an example of this mirror world of virtual reflections. In the middle is the view-independent component, and on the right, the reflection MLP captures both the large ceiling light reflection and the more subtle reflections of the chair and table legs in the polished wooden floor. Compare the combined output with the view-independent diffuse output to spot these more easily. What about the missing reflections? Well, with this model, it's easier to reconstruct reflections from sparse inputs, and so we have a more promising reconstruction. For planes, rather than second-order spherical harmonics, even outputting a scalar color is in principle sufficient for virtual location reflected point lights. But real lights are more complex, and we see increased reconstruction detail with our approach. This approach also helps on slightly curved surfaces too, in reproducing reflections from sparse inputs. Problem number 3. Rendering is slow. Now that we've split the appearance, though, we can store the diffuse component more cheaply in an octtree with only one density and 3 color coefficients, leading to a 7 times decrease in memory use over the second order spherical harmonics, but still fast rendering. And as the highlights are now less complex, we can use small MLPs for the view-dependent appearance that can fit within CUDA shared memory on modern GPUs. Together, this leads to interactive rendering at 20 frames per second for a resolution of 1280 by 720 pixels. As the geometry is explicit, we can extrapolate to render at viewpoints far from the captured views, and when we rotate the scene, we still get correct occlusion of the highlight against the coffee table. Okay, let's see some comparisons, and here, because of the scalability issue, we're just going to take the subset of photos from the scene that look at the coffee table. NERF in this case can produce high quality results with good texture detail, but the highlight is not as bright, and the rendering still takes many seconds per frame. And while fast to render, baking NERF and Planoctree's methods still struggle to generate as accurate reproductions of the scene as our method. Here's another scene. This one is physically larger with 3 rooms, and so as scalability is often a problem, we just compare to 3 other image-based rendering methods. Our approach can better reproduce the sparse reflections, such as on the floor, and such as on the thin ceiling reflection in the kitchen. Okay, so you might be thinking, but it can't be that simple, and you'd be right. One problem is how to perform the appearance decomposition and how to perform it in a way that is consistent across tiles. Remember that we only have RGB input as images. Okay, let's review our pipeline so far. We capture images and compute the global mesh using the existing reality capture software. Then we tile the space and allocate rays to each tile. Each tile has 2 MLPs, both a surface and a reflection MLP, trained using background sampling. And then for interactive rendering, we can build a voxel octatree and keep low-capacity reflection MLPs in GPU shared memory. So there are 3 pipeline components to help us produce more consistent tile appearance decompositions. The first concerns how to enforce that the appearance decomposition is meaningful. Given the global mesh, we can compute approximate view-independent or diffuse appearance images by angle-weighted averaging of the input images at each surface point. Then, along with an image reconstruction loss, we also penalize the loss between these approximate diffuse images and the output of the view-independent MLP. In this figure, we can see that this helps to remove the wood floor coloring from the view-dependent MLP's output. The second additional pipeline step relates to tile consistency. If we just optimize view-dependent appearance per tile, then there are often too few images from the sparse input to produce accurate results. So we're going to group tiles to fix this. Sparse input causes it to be difficult to even find correspondences between virtual lights, and some nearby tiles might not even see a highlight. Here, the middle camera misses the highlight entirely, and correspondence to the virtual light can only be formed between distant tiles covered by the left and right cameras. But if we include all of these tiles within a group, then the reflection MLP is able to work much better from all of these included samples. To form groups, we look for likely coplanar regions. First, we use variational shape approximation to cluster connected coplanar triangles in the global mesh. Then, given that we want to limit our reflection MLPs to be low capacity, we must bound each region of space that they're responsible for. So we use k-means to group sets of tiles from their coplanar triangle associations. Now, one limitation, given this restricted capacity reflection MLP, is that we now introduce boundaries at group edges. However, these errors can be alleviated by cross-group fine-tuning of neighboring groups. Due to the sparse input, on uniform diffuse surfaces, it's still possible to see tile edge reflection decomposition boundaries, such as here. And so as a post-process, we train a scene-specific CNN on RGB and render depth and boundary channels to reproduce the input images. This fixes many of these problems, and of course, its execution time is included within our 20 frames per second frame rate. Okay, so now that we've filled in a few more of the gritty details of our pipeline and explained all of the major components of our approach, let's now look at putting it together and seeing some varied scenes. These show reasonable reconstructions of glossy materials such as the large metal sheet door in the bottom right-hand coffee bar scene. This particular scene is over 100 meters squared in area, captured from 1,200 photographs. In terms of limitations, we still have some way to go. Consistency across tiles for appearance decomposition can still sometimes fail, and this is still a challenge from sparse input. Camera pose inaccuracy from the initial structure from motion can still be imprecise, causing blur in high-frequency texture details, and other works in this area have shown how to simultaneously optimize camera poses within the loop. Input undersampling is still possible, leading to fluffy geometry. Considering the reflections, for known perfect mirrors, we can mark them up and then render good reflections from the reflection MLP. But high gloss materials that would lead to high frequency reflections can still produce somewhat inaccurate reflections. Curved surfaces still need dense sampling, as reflected geometry is only efficient for planar surfaces. And then finally, optimization times are still quite long, even if render times are fast. And at SIGGRAPH, we'll see other work, such as Instant NGP, that could be used to speed this up. But more broadly, high quality and scalable neural reconstruction of large real-world indoor scenes is in sight. We overcome the problem of limited scene detail for MLPs by tiling with background sampling. We improve the reconstruction of reflections from sparse inputs by separating diffuse and view-dependent appearance and storing them at virtual locations. And this allows us to render quickly with less memory via diffuse octrees and small MLPs for view dependence. So as the scene videos play, we thank awards from the National Natural Science Foundation of China, the National Science Foundation of the United States of America, an Amazon Research Award, and the Information Technology Center and State Key Lab of CAD and CG at Zhejiang University. Thank you very much, and see you at SIGGRAPH.